Hello class, we are on the last section of chapter 7. This is 7.3, basis and dimension. So again, these are all things that we are familiar with. We are just going over them under a different lens, under our different definition of what it means to be a vector space. So all of the previously seen developments for basis are true for a vector space. So what we're talking about before, we were looking at in the standard Euclidean n space, okay, which is a vector space. So nothing is different, right? We're just able now to extend those ideas into non-traditional vector space. And I don't want to say non-traditional because a vector space is a vector space, but into our non-standard ideas of vector spaces. Okay, so all the things that we had before about bases are true. So there are several sort of big theorems which we're not going to go over in detail, but we'll kind of glaze over, such as the removal addition theorem. So this was the theorem that states that if you have a set of vectors that are not a basis for a space, you can add vectors to them to make them a basis, right? So for instance, if they don't span but they're linearly independent, you can continue to add linearly independent vectors until it turns into a spanning space, right? So for instance, if I have two vectors in R3, I can add a third linearly independent vector so that it spans all of R3. Okay. The removal portion of that is the same thing. If I have too many vectors, right, so that it spans but it's not linearly independent, I can take out vectors so that it is linearly independent, and then it also spans and it forms a basis, right? So again, same thing with R3. Let's say I had 5 linear, they can't be linearly independent, but let's say I had 5 vectors in R3. I can take out 2 of them or a few of them until I have enough for it to span and be linearly independent, right? So that's the removal addition theorem, okay? Again, the definition of a basis is that a set of vectors that are spanning and linearly independent form a basis, right? So spanning linearly independent set is a basis. Same definition, okay? The fact that we have unique representations of vectors as linear combinations of their basis vectors for the basis of that space is still true, right? So if a set of vectors form a basis for a space, any vector in that space can be represented as a unique vector representation of a linear combination of those basis vectors. We saw that in the last section as well. That was another theorem that was in there. This is a common sort of characteristic of a basis already, right? So that the dimension of a subspace is going to be less than or equal to the dimension of the vector space itself, right? So these are just standard things that we have from a basis. I'm sure that there's a few others that are left out that I can't think of, but these are the big ones, right? So it's really just all the developments that we've had for basis already, right? So let's look at some dimensions of some common vector spaces, okay? The dimension of Rn is n, right? So for instance, the dimension of R3 is going to be 3. I would need 3 linearly independent spanning vectors in R3 to be a basis for R3, right? So here the dimension of R3 is 3. The dimension of the real m by n vectors is whatever m times n is, right? So you just actually turn that into a product, and that's your dimension for the R m by n space. The dimension of p to the n is n plus 1. So remember, p to the n are polynomials with degree at most n. So if we're looking at p2, we're looking at all second degree polynomials and lower degree. Well, let's think about a standard second degree polynomial. It has 3 elements in it. It has the x squared elements, the x elements, and the constant elements. So p2 has a dimension of 3 because it has that constant element as well. Okay. The dimension of P, all polynomials, is infinity. Okay. The dimension of R infinity, which is infinitely a vector with infinite components, is infinity. And the dimension of linear transforms from R to N is M times N, because remember what I said before, this is pretty much the same as this vector space, right? We call them isomorphic to each other. Okay. And the dimension of smooth functions over the real line is infinity as well. Okay. So those are just the common dimensions, or the dimensions of common vector spaces. Most of those shouldn't be too difficult to remember. Just remember that the dimension of P to the N is N plus 1. That's the one that kind of gets people a lot. They'll think that it needs to be N, which it's not, it's one more. The others should be fine though, right? So let's go over a theorem. Let V be a vector space where the dimension of V is M, and M is finite, meaning it is not infinity, doesn't go on forever. Okay. And let this set of vectors from V1 to Vm, same as the dimension of V, be a subset of V. Okay. Then the set of vectors is linearly independent if and only if this set of vectors spans all of V, which is true if and only if V is a basis for V. So if this set of vectors is linearly independent and spans V, it's a basis for V. Okay, so this has to be true. The ifs and only ifs are because the dimension of V is M. I have M vectors. The only way for these to be linearly independent is if they span, and if they span, then they are linearly independent, and they span, so they are a basis. Okay, so let's do an example. Determine if this set of vectors is a basis for V, the vector space of R 2x2 matrices. Okay, so my set of vectors are 2x2 matrices because my vector space is all 2x2 matrices with real entries. So I want to know if this is a basis. So how do I know if it's a basis? I need to figure out if it's linearly independent, and I need to figure out if it spans the whole space, meaning can I create any vector in R 2x2 by a linear combination of these vectors. Okay, so what I would need is that I would need this to have only the trivial solution in order for it to be linearly independent, and then I would also need this to be able to create any vector. So I might replace this with A, B, C, D, and then make this C1, C2, C3, C4 for the spanning portion of it. Okay. However, both of those are very long-winded. It takes a long time to do that, right? To determine whether or not this is true or not, there's a lot of math involved. So let's go and use some of the methods that we know already for making these things go a little bit faster. Okay. So I can turn these into column vectors, because that's basically what my basis or potential basis vectors are, right? So as long as I create them as column vectors in the same way, meaning 1, 2, 3, 4, and this is 1, 2, 3, 4, and so forth, I'm okay. Now I could have done this a different way. I could have went 1, 2, 3, 4, and put it as 4, 2, 3, 1. That's fine as long as that's the order that I put all of the other vectors. But we know that's not really how it goes. We generally go A, B, C, and D. So just follow that same sort of direction. The point is, as long as you're consistent, you're okay, right? In the order that you put these things in. So I have this now 4x4 matrix. So I would like to make sure that it's linearly independent. I have a square matrix. I'm looking for linear independence. The easiest way to do that, right, if I'm trying to figure this out, is to do a determinant instead of setting up this matrix equation and doing REF. Just take the determinant. It's a lower triangular matrix. The determinant is 8. It's not 0. It's linearly independent. That's the easiest way to do that. The column vectors are linearly independent. These column vectors are these elements inside of this set, right? That's the easiest thing to do. And then also for span, I can say that I now have a set of linearly independent vectors. There's 4 of them, okay? So that means that the dimension of my subset is 4. And that's the same as the space that I'm in. Okay, so remember, let's come back here. I'm in the set of 2 by 2 vectors. So 2 times 2 is 4. That's how we figure out the dimension of the vector space that we're in. Okay, and since my dimension of my basis is the same as the dimension of the space that I'm in, I don't want to call this basis yet, but the dimension of my subset is the same as the dimension of my space. So that means that it spans because they're linearly independent set of the same dimension. Therefore, it is a basis for my vector space. And that's it. Okay? It's way easier to do that, talk about the dimensions, than it is to go and solve this for it being equal to 0. And then to solve this for it being C1, C2, C3, C4, and this is A, B, C, D, meaning any vector in R22, and trying to find the coefficients that way, right? So it just makes it a lot easier to use some of the theorems that we've developed so far in the class, right? So here's another example. We want to find a basis for the subspace S of P4. P4 is all polynomials of degree at most 4. But this is a special subspace. This subspace is all of the polynomials such that their derivative is 0. So I want you to think about this. How do you take a derivative of a polynomial and get out 0? Well, that means that all of your polynomials are constants, right? So P of x is this set of vectors, okay? If I take the derivative, I will get 4ax cubed, 3bx squared, 2cx, dx, and the e goes to 0. So the only way that this is going to be equal to 0, right, is if a, b, c, and d are all 0. Okay. That's the only way that my derivative is equal to 0 here, which leaves me with my original polynomials being basically all constants. Okay, so I want to find the basis for a set of constants. Well, that's the spanning set of 1, right? So any constant multiple of 1 will give me any constant, right? So the span of 1 spans S, my subspace that I need, right? So, and it's linearly independent, and it spans this subspace that I wanted. So that's my answer. So therefore, 1 is a basis for this subspace, and this subspace is all of the 4th degree polynomials and lower whose derivative is 0. First derivative is 0.